Hello, welcome to another video. So in this video we're going to talk about 2D kinematics or 2D motion, okay, the study of 2D motion. So what we've done so far, we've looked at two different dimensions. We've looked at motion in the x direction, okay, typically the x direction, so we've gone left to right, okay, so we've been going back and forth like this, and we've seen motion in the y direction. Where we've kind of defined it both up and down as positive, just to show you different coordinate systems, but we've been primarily moving up and down. So 2D motion kind of combines this, okay? So we'll have a plus x and we'll have a plus y. And this will be our, our standard Cartesian coordinate system. So how this will work for us for 2D kinematics, what we will do is motion in the x direction will be constant per time. Okay, so we are going to be examining things that move left to right constantly. Okay, so we're going to be looking at like a car driving constantly with time. So at 0 seconds, they're here. So here's our x-axis. 1 second, they're here. 2 seconds, they're here. At 3 seconds, they're here. It kind of looks like a toaster, actually. Then 4 seconds, they're here. But notice what this is like, is basically this and this change in motion, right, is the same thing. So he's not accelerating, is my point. So constant, not accelerating. So we will really only be looking at, not accelerating, only looking at systems with no acceleration in x, okay? Because there will not be a force in the x direction, okay? That said, we will be looking at, so along the y, okay, is maybe we'll be throwing a ball, like a baseball, up and watching it come back down, okay? So the ball will, its motion will track, okay? So if we were, because right now what we've done is we've kind of separate these things, right? But what if we were to actually just combine them, okay? So we were to combine the motion, if we were to combine the motion of this car, okay, with, say, the motion of a dropping ball, okay? So if you look at a ball dropping, right, if you remember when we did that, after 1 second, maybe it's like, so that's our coordinate system. So maybe after, 1 second it's here, or 0 seconds, sorry. So maybe after 0 seconds it's there, 1 second it's here, and then it starts accelerating downward because of the force of gravity. Okay. And no, the ball shouldn't get bigger as it accelerates downward. But what you'll see is if we were to create like a little grid here, and we were to go over, and we were to just, combine these two things together, so now it's a car with a baseball in it. If we were to go down, go over, we would be able to map what this would look like in 2 dimensions if some object were moving constantly to the right and accelerating downward. That's what this would map, right? And we're seeing that, what you end up getting, zoom out a little bit, what you start seeing is a parabola, okay? Right, where we're accelerating down, so the motion in the y is increasing more and more per constant time, okay? And so that's what we're going to see. We're going to see objects move constantly in the x and change in the y. Now, do keep in mind that not all 2D motion has to be constant in the x. So but they'll be like that for us, okay? For the most part, okay? There could be a couple problems out there where maybe it's like a car accelerating to the right or something, and then it goes off a cliff. But for the most part, they're just moving constantly in the x. Notice also what this means. This type of thing right here where you combine them and look at the motion. 2D motion with constant motion in x and acceleration in y, this actually shows us something pretty cool. It shows us that motion in x is independent of motion in y. And this is because, so the motion in the x direction is completely independent of the motion in the y. And the reason that is because the forces that are acting only act in the y. We're only going to have gravity, okay, for, like I said, most of the problem. And since that's a vector and that only goes up and down, and we don't have a vector acting left to right or even diagonally, that motion will be completely independent, as well as anything dependent on that force, right? So what this means for us is that if you were to drop a ball, okay, you were to just drop it, say this would take 10 seconds. So drop ball. It only has one P. If you were to just drop a ball, it would take 10 seconds to hit the ground, okay? And if you were to throw this with a constant velocity, let's say 10 meters per second, this motion right here would also take 10 seconds. Okay? so the up and down, it would hit the ground at 10 seconds, regardless of the fact that it's moving to the right, okay? So its right motion does not influence its up and down motion. So again, X motion has no influence on Y motion. Okay, and you can test this at home. You can, drop a ball and throw one out to the right, and you'll see they hit the ground at the same time if you throw it exactly to the right. Okay, if you were to throw it even a little bit diagonal, that would influence its up and down motion, and so it wouldn't fall at the same rate. And again, if you were to have a force, some other force acting, maybe diagonal or something like that, that would also affect it, okay? It's just because gravity acts up and down and that we have nothing going on left and right that, that makes this happen, okay? So, what equations are we going to use? Well, we had a few, right? Right, these were some popular ones, but what we're going to do, because, oh, and we also had the Y version of these. Okay, because there's no acceleration in X, what happens is this just tells us that V final, so these guys go to 0, okay? So this just tells us V final equals V initial, because there's no acceleration in the X. So we're only left with this equation. So our X equation is literally this, okay? And our Y equations will be all three. But there's still a couple things that are of concern. Now, the time it takes for the motion to be complete will be the same. In other words, if I throw a ball up and down, it goes up and down and hits this spot right here the same time it takes for it to go to the right and hit that spot. So time will be the same in both equations. In other words, we don't need to add a subscript to time. But the V naughts will be different, right? Because if I move into the right, that's very different. So if this V naught would be very different than a vertical V naught, right? A very different thing than an initial velocity in the Y, okay? So initial velocity and the X and Y are very different things. So we will need to add subscripts. So we need to add subscripts because V naught won't equal, so in X does not equal V naught in Y. So what we end up doing is our kinematic equations will look like this. We add another little subscript on top. Um, additionally, we add, even though there's not an equation like this, even though there's not a v final for x, I like to be consistent and add y, and sometimes you'll even see me point out a y, okay? That's just to be super explicit. Again, there is no v final over here, so you don't need this subscript, okay? But it's nice to have, and a lot of times ay is just going to be g anyway, either plus or minus g. So keep that in mind as well. But again, the time is the same, so you don't need to add a subscript to that. The other thing we need to do is, because we're now dealing in 2D space, we're going to have more than just a v0 that is only in the x, and, you know, so a v0 x like this and a v0 y like that. So what we need to do is, what do we do if we have a diagonal v0? So for example, we have a v0 that looks like this. What are we going to do? So this is our v0, right? We need to have a v0 x, and we need to have a v0 y, right? Because this is going to be v0 y. This is our v0 x. So what do we do for that? Well, we have equations, right? This is what we just did with vectors. So v0 x will be this v0 times cosine of theta, which is that angle. And v0 y will be v0 sine theta, okay? So far you have this equation, these three equations, and these two equations, okay? So instead of the original equations, okay, you've got 6 now, okay? But there is one more that also helps. So there's one more equation derived from the 6 we see, okay? And this equation is called the range equation, okay? And this guy is essentially how far something goes. So the range equation is an equation that tells you, so this tells you x final if and only if the object in question starts and ends at the same height, okay? In other words, you kick a football or launch some other sort of ball, golf ball or something. Goes up, comes down. It starts at this height, right? This is 2 dimensions. This is y equals initial equals 0. Y final is also 0. It's the same height, okay? That is the equivalent. And the x final this equation gives you is this distance. So this is your range, okay? Sometimes called r. You can also do it from a high up spot as long as it ends. So maybe between buildings or something you're kicking balls. These are the same height. And so you could do this again over here and get your x final. And the reason this equation is useful is because it saves you having to deal with vectors at all, really. So x final equals r equals v0 squared, okay? Sine of 2 times the angle. Okay, so notice you don't need v0 x, you don't need v0 y, you just need the v0 and the theta to do this guy, and g. Now, you must be wondering, there's one other stipulation here that you'll see when I derive it. If we have up as positive and gravity's negative, wouldn't this make this whole thing negative because this would be a negative 9.8? And the answer to that is no. This equation is derived under the assumption, or not even assumption, under the pretense that you've already done this and you've already made down negative, and the negative goes away in the derivation itself. Okay, so if you're curious about that. So this is equation 7. Okay, you need to know, or at least write down or work with these 7 equations. So 1, 2, 3, 4, 5, 6, 7. Okay, and this one's a special case, can only be used for same height. I guess what I'll do, I do derive this sometimes, so I guess I'll derive it now, just in case people want to see it. It's not essential, so this shows where this equation comes from. And then what I'll do is I'll talk about, so if you don't want to see the derivation or you don't find it useful, you can skip a little bit ahead in the video. I think it's useful. I think it shows you a little bit about algebra, but if you don't care, you can skip a little bit above. After that, I'll be talking about just the 3 types of problems we'll be solving, and then a couple problem-solving techniques at the end. Okay? So, derivation for this particular equation. Y final equals Y initial equals 0. Okay? This is, we insist on. Okay? This is how we derive this thing in the first place. So this is why this equation is the thing. Okay? This is how we get this equation, is we say, well, what happens when Y final equals Y initial? So if you look at this equation, this is the equation we're starting with. And if these are both 0, then, you know, they're gone. They're the same value. They don't have to be 0. They just need to be the same value. Okay? Because then, if this is 5 and this is 5, 5 minus 5, right? When you move this over, it goes away to 0. So what you're left with is 0 equals v naught y t plus 1/2 at squared. So now what you get is we can divide through by t. We have 0 equals v naught y plus 1/2 at. So come back to this. So come the range, which is the ultimate thing we're trying to solve for, is equal to x naught plus v naught x times time. Let's start at 0. So we get x final equals v naught x times time. And now let's solve the y equation for time. So let's take this guy, move this guy down here. So 0 v naught y plus 1/2 at. So we're going to solve for time. So minus v naught y equals 1/2 at minus 2 v naught y over a equals t. Okay. This is going to be essentially g, right? If we have up as positive. This is what I was saying. This will be minus 2 v naught y over minus g. And so you'll see that goes away. So this means that t equals 2 v naught y over g. And so now that we have that, and you remember this equation, x final equals v naught x times time, we can take this guy and slot that in. So x final equals v naught x times 2 v naught y over g. So now we're getting closer to our final equation. We have x final equals 2 v naught x v naught y over g. But now what did v naught x equal and what did v naught y equal? Well, they're v naught cosine theta and v naught sine theta. So let's plug those in there. So we'll plug that in there, plug that in there. And, you know, part of the reason I do derivations like this or show you derivations like this is I think they're useful for you to know. It's a good practice of algebra, okay? Especially in this class where algebra is, you know, not easy, right? So at this point, what we're going to do is we are going to pull out the v naught squareds, or the v naughts, which will become v naught squareds. We're going to have x final equals v naught squared 2 cosine theta sine theta over g. We're really close. Now, this is where, even if you were mathematically doing this, you know, you were following along, you were doing everything, you'd be like, well, I don't know what to do at this point. Which, fair enough. Unless you know the trig identity, you wouldn't be able to get farther than this. So 2 cosine theta sine theta is equal to sine times 2 times the angle. Okay, so that's where that comes from. And so once you plug that in, you get our final formula. Okay. So again, if you want more practice on algebra or, you know, something like that, I recommend spending some time deriving this guy, working towards it. Any practice with algebra is good, in my opinion, especially, again, for a class like this, which really focuses on strong algebraic skills. You really do need them to do well. Okay, so now that I've done that, I've derived all the equations. We need to do, okay, so the types of problems. There's 3 types of problems you will see in 2D kinematics, okay? You can really boil them down to just 3 kinds. There's this kind, where you're launching and ending same height, so same height. And for these, use the range equation, okay? These are the easiest type of problem for sure. The next type that you will see is up and then down. So this is above to below, okay, where your y initial is higher than your y final. There is another variance on this. I showed you going up and then back down. That's one variant. You can also just kind of chuck something off a cliff or something, and then it goes like this. This version is easier than this, okay? Anything where you're going up and down and you're crossing a path twice sometimes means that you'll, it's just more difficult, okay? So this one's more difficult. And then there's one last type. So we went from same height, then we went above to below. So we're going to go below to above. And these problems are actually the most difficult, in my opinion. So below to above. Because typically with kinematics, what you're solving for is you're solving for the time it takes to complete the motion or something like that. And if you notice with this trajectory, and this happened up here as well, right here, is you cross the same y twice. And if you remember some stuff about, you know, graphing and things like that, if you have, you know, you do something like this, you have a function that does this on the y. This is a quadratic, right? That's what a quadratic means. It means there's 2 solutions to your problem. So for us, what this will mean is you'll generate 2 times. You'll get time 1 over here and time 2, which is, this is the time you're looking for because this is the complete motion. I do typically stray away from using or trying to have problems that require the quadratic formula or whatever, but sometimes it's a necessity. So do keep that in mind that you could potentially see that as well on your travels. Okay, but those are the three types. Okay, we'll be working through those in the next video. But one last thing, there's some problem solving techniques, okay? And essentially, it's going to be the same steps that we had before, where you draw, which is set up a coordinate system, okay? There's knowns and unknowns, only now there's more of them, right? Because we're in 2D now, you're going to be dealing with not just x initial, not just x final. You'll have y initial, y final. You'll have v naught x. You'll have v naught y. You'll have acceleration in the y, which is usually g, plus or minus. You'll have time, okay? And maybe some other parts that are there, right? Like maybe you're throwing a ball up and you want to know the peak of motion, so now you have a new y to consider, or maybe you want the velocity at the final at peak, right? Which would be 0, right? Because it's going up. Velocity here in the y will be 0. We'll only have an x velocity. But yeah, you can see how it is more complicated than just 1D motion, right? But the steps to do it is the same. After knowns and unknowns, there's equations, right? And how this typically works, is you solve for time in 1, in, say, x, and plug into y, or vice versa, okay? So you solve for time in the x direction, and then you plug that answer into the y direction, because the time it takes to complete the motion in the x is the time it takes to complete the motion in the y. You may also do this vice versa, like I said, so maybe you solve for time in y and plug into x. That's usually the going rate. Sometimes it's a little more complicated than that, okay? But yeah, that's pretty much it. So we're finally getting into 2D motion, which is the culmination of the first unit. So thanks, and I'll see you in the next one.